In this video, we're going to look at the process of mathematical induction being used to prove a statement about matrices. The way this question is set up, though, is a little bit differently, though. If you do want to follow along, this is example 11 on page 203 of the Hayes textbook. But this question is set up in the format of a conjecture-style question. What a conjecture-style question is, it's something that we do quite a significant amount of in Year 12 maths methods. It's a type of question where we follow this pattern of identifying a pattern, making a prediction, and then proving that prediction. And you're going to see that structure here in this particular question. So let's look at it. So we've got this matrix B, that's equal to 2, 0, negative 1, 1. The first thing we need to do is work out what b squared, b cubed, and b to the power of 4 are. So in no particular order, as in starting at the start, we get 4, 0, negative 3, 1, 8, 0, negative 7, 1, and 16, 0, negative 15, 1. Okay, really nice and easy, just throwing it into your calculator, getting those answers out, and writing them down, basically. So very simple start to the question. We now want to try and predict the value of b to the power of n. So we're looking to write a matrix where, instead of having a value for the power, like we have here, we want to have just an n here. And, how is that going to affect each of these numbers? First thing I'm noticing is there's actually two numbers that don't seem to be changing at all. That's the 0 and the 1. So I'm going to put those in straight away because they're the same. Regardless of what n is, what power of b is, we always finish with that 0, 1. The other numbers do seem to be changing. Now, this first number, the 2, the 4, the 8, and the 16 in each of them, they all seem to be powers of 2. And in fact, it's 2 to the power of whatever the power of b is, right? 2 to the power of 1 is 2, 2 squared is 4, 2 cubed is 8, 2 to the power of 4 is 16. So I'm going to put it out there. I reckon that is 2 to the power of n. It's a little bit more complex, though, when we get to the final number, the negative 1 in there, because they're not following as nice a pattern. But what I am noticing, and this is maybe one of the nice things about working with matrices like this, is that it all seems to, ignoring the negative, it all seems to be 1 less than 2 to the power of n. Right? So 2 to the power of, let's consider this example here. 2 to the power of 4 is 16, minus 1 gives us 15. 2 cubed is 8, minus 1 gives us that 7. 2 squared minus 1 is 3. Now we need to keep in mind, though, these are negatives. So we've got the negative of 2 to the power of n minus 1. Now to me that looks a little ugly, so I'm going to write it a little differently. I'm going to write it as 1 minus 2 to the power of n. Okay, so that's my prediction for what the value of b to the power of n is, where n is a positive integer. Now we get into the proof. So using mathematical induction, we want to prove that P1, so actually no, we need to make a statement here. Pn is that 2, 0, negative 1, 1 to the power of n is equal to the power of n, 0, 1 minus 2 to the power of n, 1, where n is a positive integer. I am actually quite deliberately not referring to the matrix as B necessarily, but I am what actually is going on here in the most clear terms, and that's that this matrix 2, 0, negative 1, 1 to the power of n is equal to, we think, 2 to the power of n, 0, 1 minus 2 to the power of n, 1. So now we look at P1. Okay, 2, 0, negative 1, 1 to the power of 1, that's just 2, 0, 1, 1, so that's really easy. The right-hand side, 2 to the power of 1, 0, 1 minus 2 to the power of 1, 1. That is in fact also equal to 2, 0, negative 1, 1. So therefore P1 is true. For PK, we're going to let 2, 0, negative 1, 1 to the power of k be equal to 2 to the power of k1 minus 2 to the power of k 0, 1. I'm also going to put it out there that that's equal to b to the power of k. So I'm going to bring in the matrix notation at this point. Looking at p k plus 1, we're now talking about the matrix b to the power of k plus 1. Using matrix algebra, that's equal to b to the power of k times b. And using pk, that's equal to 2 to the power of k 1 minus 2 to the power of k 0, 1. And then b is 2, negative 1, 0, 1. So now what we're going to do is just multiply these two matrices together, see whether what we get is what we would expect b to the power of k plus 1 to be, which would literally just be b to the power of k, but with k plus 1 as the power every time we see it. When working through this, I would suggest it is really important to show the explicit multiplication process. Please don't take shortcuts at this point. This is a prove question. You're trying to show that it's, you're following the process here and that it is all coming out to be exactly what it should be. So we should be getting 2 to the power of k times 2 minus 1 times 0. We've then got 2 to the power of 1 minus 2 to the power of k. Minus 1 times 1. We then have 2 to the power of k times 0 plus 1 times 0, and 0 times 1 minus 2 to the power of k plus 1 times 1. So that's going to simplify out to, in the first element, that's 2 to the power of k plus 1. We are left with simply 0 over here and then 1 over here. Expanding out what we have over here, so we've got 2 minus 1, so that's 1 minus 2 to the power, 2 times 2 to the power of k, which is 2 to the power of k plus 1. Alright, again, I am sort of checking it as I'm working through it and making sure that it's consistent and not just, leaping to the answer with, from nonsensical statements. I'm making sure that it is correct. And in this case, it is correct because I've done everything right. So that's what we would expect b to the power of k plus 1 to be. And so now we can just make our statement. Since P1 is true, and pk plus 1 is true, whenever pk is true, Pn is true for all positive integers n. Done. That is proofs involving matrices. As always, please let me know if you would like to clarify